Okay, so we're happy to continue with the morning session on the theme of T-duality. We're very happy to have Christian from Heriot-Watt, who is going to tell us about geometric and non-geometric T-duality with higher bundles. Christian, please.
Okay. Yeah, so first of all, thank you very much, Hisham, for the invitation to be here again. I really enjoyed my display last time, and it's brilliant again to be here. So that's very nice, and the conference, of course, is brilliant, so thanks to all the organizers. So what I'm talking about is this work on T-duality. It's joint work with my PhD student, Hyung-Woo Kim, who did really excellent work on this and all the other projects that he was involved in. So if you ever see him on a candidate list for postdoc, just hire him. I mean, he's really good. Okay, so thanks to the last two talks, I think I can directly jump into the motivation. So I'll be talking about geometric string backgrounds. I will be using that. So it's a Riemannian manifold X, principal torus bundle over it in the topological case without connections, but I want to go beyond, so with connections and an abelian gerbe with connection. And then you've seen topological T-duality in the last talk already. So we have a principal torus bundle, or affine, we'll do both cases actually. Principal torus bundle over X and a gerbe on top of that total space. And then because of the exactness of the Gisin sequence, you can then reconstruct another side, at least up to isomorphisms. And then you have a dual torus bundle and a dual gerbe. And when I talk about gerbe, just think closed three forms for the moment. So this is this old work that we saw quite a few times in previous talks. And then there was this extension that we also saw in the previous talk to T correspondences, where we define the correspondence space as the fibered product of these two torus bundles. And then the condition for T-duality is you pull back one gerbe, you pull back the other gerbe, and they're isomorphic, but the isomorphism is mediated or witnessed by the Poincaré line bundle, right? This is work by Bunke, Rumpf, Schick. And how I got interested in this, I'm very interested in principal two bundles, so non-abelian versions of gerbes if you want, but generally principal two bundles. And indeed, there will be there's a lot of abelian stuff there, so it's probably a better name here. And in 2018, Nicolas and Waldorf showed that you can take this principal torus bundle that you have here and the gerbe, and you can combine this data actually into a principal two bundle for a particular two group. And this gives you this two bundle down here. The dual one can also be, of course, encoded. And the interesting thing is then that on the correspondence space, or this whole correspondence space picture, is also replaced by a principal two bundle with a particular two group. And then a T-duality is just a correspondence, a roof, a span of these principal two bundles. Right? So that's the topological part. Now, if you see this picture, then there's two obvious problems. Namely, first of all, ideally, we would want to go beyond topology. We would like to have a differential refinement so that we can talk about metrics as well and have the full T-duality, really. The first problem. And the second problem is this old problem about what about non-geometric backgrounds. So in their work, Nicolas and Waldorf deal with T-dualities between F2 and F1 backgrounds. So they do get topologically the T-folds. And at least, well, in these correspondences. And so the question is, can we go a little bit beyond? So can we really do, at least have a proposal for a description of T-duality between arbitrary non-geometric backgrounds, right? And the story here is that you have all these different string backgrounds, and you know what the T-dualities do in each case. F2 is where you get the geometric string backgrounds. Under T-duality, F1 is then you get these Q spaces or T-folds. They're locally geometric, but globally they're non-geometric. They're glued together by T-duality transformations or elements of the T-duality group. And then there's also these F0 backgrounds where they are not even locally geometric, they're completely non-geometric. And the question is, are there at least candidates for extending this picture to this situation? So why is this interesting or hard? Well, first of all, we had this roof or correspondence of principal two bundles where we combined the principal torus bundle and the gerbe into one big object. The differential refinement that we need for describing metrics, and the metrics will come from a Klutzer-Klein metric on the principal torus bundle and the metric on the base, is that we need connections on these principal two bundles. And for them to make sense, is you need a little bit of additional technology that we call adjustment that is not that widely used or spread throughout the literature. And I'll explain this in a little bit more detail. The problem with non-geometric backgrounds is not a problem. It's more that you have to go beyond principal two bundles. So in their picture, Nikolaus and Waldorf did the topological part, and the topological part you can just capture by principal two bundles. But if you go beyond that, if you have differential refinement, you expect scalar fields, and therefore you need to go to groupoids. And if you go to the R spaces, you expect actually also something like -1 forms that have global curvatures. So then you go to augmented groupoids, right? These are the key ingredients to answer these two questions. And these are interesting to study. Essentially, my motivation for doing this is to get more examples of principal two bundles with adjustments that are useful in the literature, because this is still a little bit unclear where it comes from. Okay, so the outline is I first review adjusted connections on principal two bundles. I give a derivation or motivation for where they come from, just an overview over this, and it's all very down to earth. Then I give you some examples. Also, the challenge is now to make connections to this diagram that we saw before. So I have to talk a little bit about higher instantons. And then I show you an example which you may be interested also from a physics perspective, namely how to get the curvatures of gauge supergravity in a very, very nice and elegant manner. But then I'm done with this, and then I switch to geometric T-duality, explain how this works with principal two bundles. That has been verified that our construction indeed works, and it matches all the expectations that I can think of. And the really nice thing about this construction is that everything is incredibly explicit, right? So usually when you work with higher structures, they package up a lot of information, and unpacking this information can mean quite a bit of work until you're down to a level where you can work with concrete formulas. But here, everything is incredibly explicit and also fairly simple, right? So this is what I like about this. Okay, so I give a couple of examples, and then we'll talk about the, if I have time, non-geometric T-dualities, the Q spaces, and the R spaces as well. I should say I don't claim to be an expert in T-duality at all. I came from this principal two-bundle direction into that, so both questions and comments are very welcome. So if you see anything that you would like to see verified or tested, or have any thoughts or any contradictions, right, God forbid, then just let me know. Okay, so principal two bundles or non-abelian gerbs with adjusted connections. I've talked about this already last time a little bit, so just a very, very quick overview. So you know that principal bundles with connections are essentially geometrization of the data that you need for one-dimensional parallel transport in terms of connections that we are happy with to work physically. Then if you do higher dimensional parallel transport, there's lots of argument that tell you have to go to higher or categorified geometry. So you get a higher or categorified gauge group, whatever that is, right? So you higher categorified spaces, higher groupoids. And the connections then lead to the higher degree form fields that we know from string theory and supergravity, like the B field, the Capramont B field, and all the other forms that we know from supergravity. And so then you can define principal G bundles in different ways, and all the different ways have essentially categorifications. But one direct way is you describe it in terms of co-cycles. So you have some manifold, you have some atlas over it, so it gives rise to surjective submersion. From that, you construct what's called the check groupoid. And then you consider a bundle just as a functor from the check groupoid into this delooping of your gauge group, right? That's very down to earth, and you get explicitly the transition functions, the co-cycle relations, and so on. And equivalences, bundle isomorphisms are just natural isomorphisms. So this picture is trivial to consider for higher groups here as well, and then you get higher bundles, right? So in this way, you construct the topological part of higher principal bundles in a direct fashion, and there's no problem at all. Then you can work a little bit harder, and then you get also connections. And I think one of the first papers are probably these by Breen Messing and Aschieri, Cantini, and Pragnot, who's in the audience, from 2005. And the data that you obtain there for a two group looks like this. Don't worry too much about the details. The only interesting thing to see is that, I mean, here you have the traditional co-cycle data for principal bundle with connection, and you just have one step up, you have corresponding data that glues these things together. And in their paper, they also found this weird delta thing, and it sticks a little bit out, and it's a little bit unnatural, because usually you want to trade one form degree for 1 degree in check cohomology, right? So for the number of overlaps over which you are here, the transition functions are of double overlaps, right? And I can go, so in the categorified case, I have triple overlaps, 0 forms, over double overlaps, 1 forms, and over the patches themselves, I have 2 forms, right? But this here sticks out a little bit strangely, right? In most of the later work on principal two bundle, like Baez, Schreiber, and Hisham, and Urs, right? So that was dropped later, and the price that you have to pay for this, that a particular part of the curvature actually must vanish. And that's a little bit a problem that makes them problematic for uses in physics application. For principal 2 bundles, the so-called fake curvature, that's the nomenclature of Breen, needs to vanish. That's a combination of the ordinary expression for the curvature 2 form that you would use, and the addition you add the B field can show that this is a natural object to consider from a higher geometric perspective. And if you don't impose this condition, then higher power transport is not repolarization invariant. That has been shown by Urs and Konrad Waldorf a long time ago. And also, if you look at the closure of the gauge transformation and composition of co-cycles, whichever you prefer, it's both equivalent, then you get this additional condition. So that's unusual. That's not something that appears for principal bundles. You get a condition on the curvature form itself. So this expression has to vanish. Otherwise, your co-cycles don't glue together. So the co-cycles conditions themselves, they restrict also the curvature in a particular way, right? And furthermore, if you're like me interested in M5 branes and self-duality in 6 dimensions, then the self-duality condition is not gauge covariant in this framework, right? If you don't impose f equals 0, because the gauge transformation is here in a nice covariant one, and then you have this fake curvature with a lambda, but this will break self-duality generically, right? So you need to impose this, otherwise there's a problem. But if you do impose this condition, you run into other problems. The first one is not that important, but these higher connections can always locally gauge transformed away, so that you're only left with an abelian gerb locally, and that's not so nice, right? Of course, I mean, we went through all this work of constructing non-abelian gerbs, non-abelian principal 2 bundles, or generalized principal 2 bundles, to go away from abelian gerbs, right? But if you impose this fake curvature condition, you're back down to abelian gerbs locally. And I think this is actually the reason for the lack of popularity of non-abelian gerbs in string theory of these principal 2 bundles, because people observe this in informal calculations. You get this very, very quickly. And then, you think that they are useless, essentially, or for many purposes not that useful. But there's a solution, and that solution is rather, well, I mean, it's inspired by work of Urs and Hisham, and they worked it out in a special case, but you can do that more generally, and you can also do it in the finite case, so for actually full 2 groups. So whenever you have a 2 group, then there's a particular map which we call an adjustment. So that's a map from this 2 group and the Lie algebra of this 2 group, or the Lie 2 algebra of this 2 group, into the Lie 2 algebra of this 2 group. It satisfies a particular condition which we are currently studying further. So that has some interesting properties, but we are not completely done with it. And if you have this map that satisfies this condition, you can actually change. You can modify the notion of the curvature on a non-abelian gerb, on principal 2 bundle, in such a way that all these problems that you had before evaporate, and they all go away, right? And moreover, this map is well known to appear in supergravity. So this map is there in physics. We know it from physics already that it's there, so we would expect that this exists. So it's an additional algebraic datum. It has nothing to do with the principal 2 bundles. Well, has something to do, of course, but it really comes from the gauge 2 group. It's really datum on the gauge algebra, gauge group itself, and necessary for the consistent definition of invariant polynomials. I think this is how it entered also the work of Hisham and Urs. And it then specifies a strange delta that we had before in terms of G and F, in terms of part of the co-cycles of the non-abelian 2 bundle, right? So this is actually quite natural, and you get a modification of the curvature that induces a modification of the co-cycle and co-boundary relations automatically. And then this annoying fake flatness condition all drops. You can drop it, and it all goes away, and everything becomes nice. And you match a lot of expectations that you had from physics. So as an example, just to make contact with the diagram before that we had, you all know the fundamental SU2 instantons are regarded as this Hopf vibration S7 over S4. You can double the SU2 group to spin 4. Then you get this spin 4 bundle, spin 5 over S4, regarded as the quotient spin 5 over spin 4. And so you have a natural doubled instanton if you want. You can arrange it that, the second Chern number vanishes in this case. And so therefore you can lift this to a string bundle. And so that's just you regard S4 as string 5 over string 4. And then you have a natural string 4 bundle living over it, right? So it's non-abelian gerb. And if you work out all the co-cycles, they're indeed of this adjusted type, right? So the curvature is not vanishing, and the fake curvature is not vanishing, but it satisfies this adjusted co-cycle condition that you get if you modify the structure. Okay, so let me just give you a few more direct application. So the one example that you probably all know, it's from heterotic supergravity. So there you have a particular gauge structure which it's a string Lie-2 algebra in the skeletal form. So you have spin n, and then you have an additional abelian factor, which is essentially the B field, and that's your non-abelian gauge algebra that you have in heterotic string theory. The gauge potentials are one forms with values in spin n, and two forms. These are the curvatures. And now if you just did the usual non-abelian gerbe story, you would get the blue part of this stuff, right? So you would just get here this blue part. But there's something missing. We know that this is not the correct this is not the correct 3 form, but the correct 3 form is obtained after you correct by this term. And then these two terms just combine into the Chern-Simons 3 form, right? So this term in particular is not one that you would obtain in the usual discussion of non-abelian gerbes. You get the usual Bianchi identities that you know. So that's been known. I mean, they didn't write it, they didn't phrase it in these terms, but it has been known in the supergravity literature. It dates back to 82 and 83. They obtained these formulas. And Urs and Hisham, of course, they made this rigorous and put this into appropriate context, right? But then you can generalize this, and let me quickly talk about this because it's very interesting, I think, from the perspective of supergravity, and also shows you that this is not just a one-time example, but this is actually a general principle that underlies all these higher form curvatures. So there's something interesting called the two-term EL infinity algebras. I mean, L infinity algebras are quite popular by now, so I should probably don't have to mention them too much. But there is an extension. So L infinity algebras lift the Jacobi identity up to homotopy. And in these EL infinity algebras, you also allow for the alternator, so antisymmetry of the Lie bracket to be lifted up to homotopy. And that's a nice idea. And Reutenberg did this for two-term EL infinity algebras back in 2007. So yeah, you have the Jacobi identity and the antisymmetry up to homotopy. So you get this epsilon 3, which leads to the Jacobiator then, and the alternator, which captures the antisymmetry. And the observation is just in the example of heterotic supergravity that we saw before, the adjustment that we saw at the level of algebras is just the alternator in this particular two-term EL infinity algebra for the string Lie-2 algebra. And the idea is now to generalize this, right? So the idea is we don't quite know where the alternator comes from or what precisely it should be, but we know that in examples at least it's the alternator of an EL infinity algebra, right? Because it's additional algebraic structure. It's a structure that's not in the gauge L infinity algebra. You have to put additional algebraic information in it. And in the EL infinity case, we do get this additional algebraic datum. Okay, so you can generalize this. We had a paper on EL infinity algebras. There's still a minor problem, so let me talk about what definitely works. So you can generalize just the previous discussion. Instead of saying that you just use two-term chain complexes, you extend it to Z-graded chain complexes, right? So and you say, okay, I have one lift of the antisymmetry and the Jacobi identities, then you get what we call E2 L infinity algebras. And they're the homotopy algebras of the H Lie-2 algebra. So H Lie-2 algebras are just a cochain complex, a Leibniz type product, and an alternator that controls the antisymmetry of E2 0, right? So if the alternator is 0, then I just get a differential graded Lie algebra. And here I lift the antisymmetry of the Lie bracket to have an alternator. And now there are two theorems that are important that we proved in this work in 2021. Whenever you have a differential graded Lie algebra, you can shift truncate it to get one of these H Lie algebras, and then you can antisymmetrize them to get an L infinity algebra. So the combined operation from DG Lie algebras to L infinity algebras, that's worked by originally Fiorenza and Manetti, and that was rediscovered by Getzler further. So we just refined their theorem in a way. So we have one thing in between, which is this H Lie-2 algebra. But this H Lie-2 algebra is now important because it has these alternators in it. And these alternators, and that's the second theorem that we have, they give you adjusted connections. And they give you exactly the adjusted connections that you expect. Namely, if you look at the so-called tensor hierarchies in gauged supergravities, so they have lots of higher potential form fields. They have 1 forms, 2 forms, 3 forms, and so on. And they construct them in a rather pedestrian manner. So they see that certain things don't close. You introduce new things to correct for that. These things don't close, and so on. But what you can do directly is the following. So gauged supergravities come with an underlying differential graded Lie algebra. You use our construction to construct the corresponding H Lie-2 algebra from that one. And then you automatically get the right connections and curvatures for gauged supergravity, right? So it comes directly out as you would expect. as adjusted connections. This is important, of course, if you want to consider supergravity theories on arbitrary manifolds so that you can glue things together globally. And there's an example. So you have here the various representation spaces of E66 that form the tensor hierarchy, or that underlie the tensor hierarchy for 5-dimensional maximal supersymmetry. And you get then an H-Lie2 algebra out of that, and then you use our formalism, crank a wheel, and you get adjusted curvatures. You look it up and compare that to the physical literature, and these are exactly the curvatures that they get out, right? So this whole formalism of adjusted connections from alternators matches gauged supergravity. So that looks good. Now what we need is actually, we need more examples to see where the adjustment actually comes from. And this was the motivation for looking at T-duality. So let me first review briefly this nice picture by Waldorf and Nikolaus, because it's a really, really beautiful picture. I think there's also some inspiration by other people as well. First of all, there's a particular 2 group they call TBNF2, and any string F2 background is essentially principal TBNF2 bundle, right? So whenever I have a principal torus bundle and I have a gerb on top of it, topologically I can encode this into a TBNF2 bundle, which is nice. So a principal 2 bundle I have here for each string background. And what TBNF2 is in detail doesn't matter. It will vanish essentially from our discussion immediately. But there's an equivalent, well, at least the topological bundles, 2 bundles that come out of it are equivalent, a 2 group TDN. And this looks as follows. It's incredibly simple, and this is why I write it down. So it's just R2N as the objects, and these are the morphisms. R2N, Z2N, U1, right? And all the maps are incredibly simple and incredibly explicit, right? So there's no complicated computations, a little bit of linear algebra that you need to do. And that's all there is, right? Why I highlight this is also that I want to draw your attention to this additional little map here. There's a bilinear form between 2 elements, between these R2N and Z2N actually. And this linear map will be, as you may already guess it, this will serve as an adjustment, right? So this is already built in the 2 group TDN. So there's an adjustment there. Now the interesting thing is you get a double fibration of 2 groups. So there's a map from TDN just down to TBF2N. And then there is also another map that you can construct, because on TDN itself, there's a flip automorphism that maps TDN to itself. And I can first apply flip automorphism and then this projection, and then I get a second projection down to TBF2N, right? So I have this TDN on the top, and I get 2 maps down to TBF2N. And this now automatically induces a double fibration, roof, correspondence, span, whatever you like, of principal 2 bundles, right? So here's my TDN2 bundle, and then the 2 groups, the double fibration in the groups induces also automatically maps between these 2 TBNF2 bundles. And this is the construction of Nikolaus and Waldorf, right? So this PC is a principal TDN bundle. These 2 are principal TBNF2 bundles, so they correspond to F2 backgrounds. And yeah, so the important thing again is that the gerb, so this 3-form and more information that you have there, they combine into 2 bundles of this type. And this describes geometric F2 to F2 topological T-duality, right? So that's their work. Yeah? Well, because they showed that this condition that if you pull back the gerbs to the correspondence space, that they're isomorphic, and the isomorphism mediated by the Poincaré line model is satisfied in this case. Okay, for me, T-duality is exactly this picture by Bunke, Schick, and so on. Okay, yeah, maybe. We should talk about more what else you would expect. This is exactly the kind of feedback I'd like to hear. Yeah. Mm-hmm. Yeah, I mean, what I'll show you is that our differential refinement produces. They have the. Okay, so they reproduce Bunke. What is it? Bunke, blah blah, Schick, right? They reproduce precisely this, right? And what our construction will do, you'll see that later, is we reproduce the Boucher rules. Right, so if that's, I mean, the string theory would be happy at that point. You may want to demand more, right? So, but we should talk later about this. Okay, so now the full picture. So essentially, Konrad came over for Viva, and we talked about this. And the problem was that they didn't know how to put differential refinement on it, and that's not surprising because they didn't have this adjustment technology. That's the key to doing that, right? So as I said before, TDN, this 2 group, has a strange bilinear pairing in there. And that's a very natural adjustment map. And that's actually the adjustment map for the group itself, so that for the 2 group itself. So that's the finite form of the adjustment. And we can define adjusted connections on these principal 2 bundle. There's an interesting observation that this TBF2N does not. So it's not completely clear what that means. But at the other end, you can show that any TBF2N bundle is equivalent to TDN bundle, and then you can adjust there. So it may be that for adjustment to work, you need to go to a large enough equivalent 2 group. Okay, so what we have is the full topological and connection data on PC. And once you have this, you can reconstruct the gerb and bundle data on these 2. So once you describe these bundles, you can reconstruct the individual string backgrounds that should make up the T-duality pair. And then what we also did, because it was so simple, is we generalized to affine torus bundles. And affine torus bundles you can interpret as GLNZ times U1 to the N bundles, right? And then you just get this group here. Okay, so we wanted to verify this, and there's 2 ways. I mean, first of all, you can do a very cumbersome long calculation to reproduce the Busher rules. Because of time constraints, we didn't do that, so we wanted to look at least at examples. And the fancy example, the fashionable example is, of course, these 3D Near manifolds. So they are principal circle bundles over the 2 torus with a particular Chern number, K. And, well, you have explicit formulas for all of these. You know what the local connection form should be. You know the Kaluza-Klein metric, what all this looks like. Of course, you can write them down, and they're very simple. And then, of course, you have gerbs characterized by this integer, by the Dix-Meduardi class. And yeah, so topological T-duality, what it does, it exchanges the Dix-Meduardi class of the gerb with the first Chern class in this fashion, right? So now let's see if we can capture this with our description. Because actually in Nikolaus Waldorf, they didn't have examples in there. That was a little bit, but yeah. So we try to fix that as well. Yeah, so that's the picture, right? So we need to give data for a principal TDN bundle. Here the Li2 group is TD1 because we have only one T-duality direction. And then the explicit form is not that important, but you can write everything down explicitly. I mean, there's nothing left open, there's nothing hidden or so. So these are just the co-cycles for this TDN bundle. These are the topological part, this is the connective structure connection. And you see that the Dix-Meduardi class and the Chern number, they appear very symmetrically. They appear perfectly on equal footing here. And interesting, the U1 Gerby part here is kind of almost redundant. It's just a consistency condition that you can glue things together properly. And that's exactly what you would expect for these TDN bundles, right? And then you can reconstruct both string backgrounds fully, right? So this T-duality for this Neal manifold example is fully captured in our story, not a problem. And then Konrad, after our paper appeared, he did up this work, and he wanted to provide a slightly different perspective also on T-duality, but it's essentially equivalent to what we did, and he reproduced the Busher rules locally. So he really showed that our approach, so these principal 2 bundles with connections, give you locally the Busher rules, and this is exactly what you would expect from the string theory perspective. Right, so we have a full description of this geometric T-duality, at least to the extent that I would like. With non-trivial topology, right? So you can now do T-duality over arbitrary spaces, where the arbitrary gerbs topologically, and this glues together. Okay, so that's already quite nice. Another nice thing is that if you know T-duality, you know that there's this T-duality group GONNZ or ONNZ, right? Here we use GONNZ. Actually, I should talk about that as well with you, Mattei. And how does that come into the game? Well, by abstract nonsense, there's a natural definition of morphisms of 2 group. There's an automorphism 2 group of a 2 group. That's also given. There's a 2 group action. All of this you can define rather directly, or you just look it up in the literature. That's not a problem. And then you can compute the automorphism 2 group for this TDN, for the strange thing that's there. And then you see that this is a 2 group that has GONNZ in there. But you do need to extend this. And this is actually interesting. I'm not quite sure what this means completely. You do need to extend this non-trivially to a 2 group. And we provided the detailed expression for these, what it really looks like, how you can compute with it. You can write it down explicitly and compute with it. So GONNZ itself does not act on TDN, but this 2 group, this extension, actually does. And I'm not quite sure, as I said, what this Z2N really does. So that's one of the open ends, many open ends in this project. So we recover the T-duality group for affine torus bundles as well. And then what you have is you have the explicit action of the geometric subgroup, the B, beta transformation, T-dualities, they all act as endo2 functors on this TDN, and therefore also automatically on the TDN bundles. So all of our constructions are automatically fully covariant under this T-duality 2 group that we found here, right? So everything that we do now from now on will be GO and NZ covariant, and therefore we automatically have, like in double field theory, manifest GO and NZ covariant formulation. Okay, and that will become important now, in particular, when we go to non-geometric T-dualities. And now I have to say, this is a proposal, right? This has not been verified. It matches everything that it matches the construction of Nicholas-Waldorf in the topological case. And we can reproduce examples, but beyond that, it hasn't been verified, right? So that's a proposal. So far, we had only geometric T-dualities between F2 backgrounds. And then you can recall the classification of these backgrounds. So, I mean, you have this F3 background. But you see, as soon as you have T-dualities along two legs of this H, you get Q spaces, you get T-folds that are locally geometric. And three legs, you get the R spaces that are non-geometric. And so how do we attack this? Well, the observation is that T-duality is essentially a Kaluza-Klein reduction. And you find this in the literature. Of course, I first heard it from David Berman back in 2015, 16, around there. And of course, it's in Luigi's work as well, and in Hisham's and Urs' work. So it's kind of clear because you do fiber integration, right, as you saw in Hisham's talk, in Matthias' talk as well. Okay, so if we regard it as Kaluza-Klein reduction, let's become a physicist, and we have a B field. If I do one T-duality, so one-dimensional reduction, I get two forms, one forms. But if I do two T-duality directions, of course, the B field produces two forms, one forms, and zero forms. So I have to do something more. And what can I do more? Well, instead of just having a principal 2 bundle, which will give me 2 and 1 forms, I need a Lie 2 groupoid bundle, which will give me automatically 2, 1, and 0 forms, right? There are scalar fields. There's a manifold of scalar fields. And they will extend the 2 bundle to principal 2 bundle to a Lie 2 groupoid bundle. Now, if you have 3 T-duality directions, you get 2, 1, 0 forms, and also some -1 forms, which clearly don't exist, right? But -1 forms we can still regard as a global. Well, if you thought about curvatures, then -1 forms would have globally defined curvature 0 forms. And these, of course, still make sense. And that gives us then the motivation to go to augmented groupoids. And I'll talk about this a little bit later. Okay, so translation to mathematics, as we saw, if you just have 2 forms, it's an abelian gerbe. If I have also 1 forms, then I have a principal 2 groupoid bundle, right? So 2 group gives me 2 forms and 1 forms. If I have also 0 form fields, so scalars, I get principal 2 groupoid bundle, and additional -1 form field, psi field, gives me principal augmented 2 groupoid bundles. Okay, so everything, just these are the ideas, right? And now what we have to do is we have to work this out and see if we can actually make all of this work, right? So in particular, where do the scalars live, right? So we get the 2 from the 2 T-dualities, we get the scalars from the metric and the 2 form. And these scalars should live in this Narayan moduli space, right? So just this double quotient. And so how do we incorporate this into the 2 group to get the principal 2 groupoid bundle? Well, this is double quotient, and here we have the T-duality group, right? So what we do is we just consider this space, and instead of quotienting by the T-duality group, we kind of do this derived geometry trick, right? And we put this into an action groupoid. So instead of looking at this quotient, we just look at this action groupoid, right? So we have Qn here, and we have here the action of GO and NZ on Qn, and that's equivalent to looking at the quotient. It's just a resolution like we do usually in gauge theory, right? So that we don't have to work with quotients. Okay, so this also has the advantage that we can now, in a nice way, extend this action groupoid to a full Lie 2 groupoid, because well, over each point of Qn, over each point of the scalar manifold, we can now put a TDN fiber, right? So this 2 group we had, we can put over each point of the scalar manifold. And then what we do is we take this GO and NZ action, lift it to this 2 group action. And remember, this 2 group was acting on TDN and kind of take the diagonal action of this, right? So we have a scalar manifold. Over each point in the scalar manifold sits a 2 group as a fiber. And then we have the quotient by GO and NZ, and we know how this acts on the scalar manifold and on the 2 group part. So we take the diagonal action, and the result is then this Lie 2 groupoid, TDN. Okay, and then T-duality, our proposal is the following. T-duality for involving general T-folds on both sides is nothing but a TDN bundle. Right? So non-geometric T-duality is simply TDN bundle. Yeah, and the interesting thing is then the T-duality group actually becomes gauged. Right? It doesn't introduce new connections because, of course, it's a discrete group. Right? There's no new connections. But it does appear in the transition functions how things are glued together. And that's, of course, important in T-folds because we know in T-folds the local geometric data is actually glued together by transformations of the T-duality group. Right? So this is exactly what you would expect. We can reproduce the topological discussion in Nicholas Waldorf that they had, right? Remember they had the T-duality between F2 background, between a geometric background and a non-geometric background. They had this at the topological level, and our discussion reproduces that. But again, we have a differential refinement for these Lie-2 groupoid bundles, right? So we have connections on these, so we have the full picture. There's nothing missing from it in principle, right? So this may, as I said, and more checks are needed to describe all T-dualities between arbitrary pairs of T-folds at the topological level. So arbitrary topologies and everything is defined to glue together nicely globally. And that leads to an interesting question, namely to describe Q-spaces T-folds. Instead of using non-commutative geometry, right, there's this picture of describing T-folds as vibrations of non-commutative tori over a circle. You can just use higher geometry, right? And this might be more comfortable. Who knows? Okay, so the example that you can study there is a usual one. So you have a 3 torus with H flux. You do 2 T-dualities, and you get a T-fold. This is one of these famous examples that are around. And the gauge groupoid would be here TD2. Because we over T3, we have 2 T-dualities. The base manifold is just S1. So because of the topology, all data over trivial overlaps is trivial. We have no Tn bundles over S1, so there's also a lot of the data is trivial because of this example. But what remains as the scalars, Q, and transition functions for the scalars in the T-duality group. And well, I mean, they satisfy the transition functions for Lie groupoid bundles, so think gauge sigma model or something like this, right? With a discrete gauge group, so it's not quite the same. Okay, so we know from our dimensional reduction that we expect 4 scalar modes, namely the metric along the YY, YZ, ZZ directions, so the 3 components of the metrics in the 2 dimensions that we reduce, and the B field in the YZ direction. And you can arrange them into these 4 scalars that you get, and this is exactly what our formalism says you should get. And then you get the T-fold as by the transition functions that are exactly of this form. And you can show that this glues together nicely. I mean, you will arrange these in the form of a generalized metric, and then you have the T-duality group acting on these, and you can show that things glue together exactly as you would. Right? So the T-duality group acts on these co-cycles exactly as expected. So we can reproduce this particular example at least. Okay, so this was quite entertaining, and then we thought, why not go further? And I mean, so far we were quite in a reasonably good domain because T-folds, Q-spaces are still locally geometric, so they're relatively harmless. But R spaces are not even locally geometric. So how does it work? Well, remember our motivation for going to Lie-2 groupoid bundles. Now we have this additional -1 forms after 3 T-dualities, which have global curvature 2 forms. And the way to look at global 0 forms, right, they are not patched together anymore, they're globally defined, is that you should actually look at an augmented Lie-2 groupoid bundle with connection. And let me briefly mention how you do this. So first of all, to do these groupoid bundles for the experts, well, of course, what you do is you describe them as Kahn-simplicial manifolds and higher groupoid one-morphism or simplicial maps, simplicial homotopes, right? You go to this simplicial framework, and in this framework, our check groupoid that we always use to define principal bundles, principal 2 bundles, was usually everything above this line, right? So we had patches, we had double overlaps, triple overlaps, and so on, all the way up. We considered a morphism essentially in the delooping of our gauge group. Yeah, if I cut this up above, then I get exactly Lie-2 groupoid bundles in, well, I mean, there's a few errors. Well, no, this is the data, right? So I get Lie-2 groupoid bundles in the simplicial picture. And now remember, we also need global functions, global scalar fields to describe our -1 forms with global 0 form curvature. So in the check groupoid, instead of ending here at 0 simplices, I can go one step further to -1 simplices because I have the surjective submersion that defined my check groupoid in the first place, right? So there's a natural map that I extended by. And correspondingly, if I extend the delooping, or if I extend my Lie2 groupoid by one additional element of -1 cells, I do get these globally defined globally defined 0 form curvatures of -1 forms, right? So this is kind of the natural thing to do in this case, I guess you would expect. And it's also interesting that it terminates here, right? There's nothing more that you can do. And this is also where our T-duality ends, right? We have T-dualized along 3 directions. The 3 form has been completely T-dualized away, right? So it ends here mathematically and physically, which is encouraging. Okay, so then you can construct TD and org. And just as before, where we asked ourselves, where do the scalar fields actually live? And we used the Narayan modular space as the answer. Now you have to ask, where do this additional 0 forms live, right? So they are these R fluxes, and we have to see what we actually parameterize these R fluxes. And then you look at the literature, and then you realize that in these tensor hierarchies that I mentioned before in supergravity, right? These tensor hierarchies of lots of gauge potentials with these adjusted curvatures, the R fluxes actually correspond to embedding tensors at the infinitesimal level. Right? There's a datum in gauge supergravity called the embedding tensor that tells you which subgroup is gauge. And now if you take this embedding tensor and you integrate it, so from the Lie algebra level to the Lie group level, you should actually get all the R fluxes. So we claimed, I mean, not physically motivated, I mean, this is a proposal, right? It's speculative. That you integrate the embedding tensor, that gives you a nice moduli space for your scalar, for your additional scalar fields. And you define this. And then everything, once you decided on this answer, that this is the answer that you want to have, everything is fairly straightforward because the T-duality group acts in a very, very nice and natural way on this modular space of integrated embedding tensor, and you just write down the co-cycles, right? So it's not particularly difficult. So you have then these augmented Lie2 groupoid, TD and AUG, and you then just define the TD and AUG bundles as well, right? And you literally just write them down. There's not a problem. So what do we check for these consistencies? Well, the moduli match. You do get the right R fluxes that you would expect, kind of by construction, because we did this up here. All previously discussed cases, everything that we did so far is included in this, right? I can restrict TD and org bundle to get TDN bundles, both as a Lie2 groupoid and Lie2 group, right? So this is this contains all the previous cases, right? So I just need to restrict this and I get everything that I discussed previously. And interesting, and I'm not sure what this means, but maybe there's some answers in the physics literature. You do get consistency conditions between the Q and R fluxes from the co-cycle relations, right? They're not arbitrary. There are certain relations that are forced upon you. And yeah, these should certainly be studied further. Yeah, and so the upshot of this, the interesting point is, in order to describe R spaces, instead of using non-associative geometry, that is popular, maybe one answer, one way of answering it, lifting the non-commutative geometry that we saw for T-folds, you may simply be able to use higher geometry, right? So you might simply be able to get away with TD and org bundles. At least it's a proposal that makes sense and is well-defined globally and reproduces the examples, or some examples that we know. Okay, so let me quickly summarize because I'm between you and lunch, essentially. So what has been done is, well, previously Nikolaus and Waldorf told us that topological T-duality can be described using principal 2 bundles, combining again the torus bundle of the background and the gerb into one big principal 2 bundle. And then, because we know this technology of adjusted curvatures, we were able to differentially refine this, extending it essentially to full T-duality. So their construction is contained, but of topological T-duality, but we could refine it, and locally it does reproduce the Busher rules as you would expect. Everything is really explicit. You can calculate with these things. That's not very abstract. It's not hard work to tease out what these things are. And in the process of doing that, we found that the T-duality group arises from the automorphism group of the structure 2 group of these principal 2 bundles. And it is really a 2 group. So that's the first interesting question. Why is it a 2 group? What does this additional factor of Z2n have to do there? And then we went beyond the geometric cases and came up with two proposals for Q spaces or T-folds using two groupoid bundles, and R spaces using augmented two groupoid bundles. And again, the R space case contains everything, subsumes everything that was before. So what do we want to do in the future? Well, first of all, we should link some mathematical results that we have, namely this T group, the T-duality group, the conditions between Q and R fluxes, and a lot of other things to physical expectations, and see that they match. And in particular, if you have any tests that you would like to see be done, just let me know, right? And yeah, then there's lots of other things that we should link this to, the NQ manifold pictures for double field theory in particular, because double field theory is this theory where you try to make everything O, N, and Z manifestly covariant. Our approach is manifestly O, N, and Z covariant, so we should be able to make an interesting and strong link to double field theory. We may want to think about non-abelian T-duality, so Poisson-Lie T-duality and these things, because we know in principle what this means at the mathematical level. So the adjustments there are there for the string two group, for example. So we should be able to make some statements. But then to link up to the title of the conference, of course, which is M theory in mathematics, not string theory in mathematics. Our next step is, and this is what we're working on at the moment, being distracted by a lot of other projects as usual. This is to attack U-duality, and we have some ideas how to approach that as well in this framework. Okay? Yeah, thank you very much.
Thank you, Christian. Questions for Christian?
Mm-hmm. Yeah.
What's it? Oh, sorry. Take the T. No, you don't need to look at anything.
No, I'm just showing you. I'm not looking.
The 3 torus with H flux.
Yes, yeah.
So it's got 0. It's got all the components.
Yes.
Right, and
yes.
It's got the 0 component also. So I'm thinking of the 3 torus over point.
Yes.
Okay, what's the T-dual in your setting?
Well, the T-dual is described by this corresponding TD3 bundle. Well, it's just an element in TD3, right? So there are co-cycles over point. Well, it's this case, right? So it's this, you have an R space,
case, yeah.
right? Yeah. And you look at TD3 org. You write down what this is. It's not too hard, and you just the co-cycle, the constant co-cycle data essentially. I mean, of course, a lot of this stuff is trivial, but you still get R fluxes, you get the scalars, and so on. So there's something non-trivial there.
You haven't worked it out exactly, is it?
Well, it's trivial to do. I mean, it's you essentially get a point in the modular space for R fluxes, and you get scalars in the Narayan modular space in 3 directions. But because you started from the T3, these will be trivial. So you just get an R flux in our case, right? That's what comes out. Yeah.
So my question even before was
yeah.
T-duality is not just this Job data.
Mm-hmm.
It's also you have to know what the something like the charge group and
mm-hmm.
an isomorphism of the charge groups
yeah.
on each side.
Mm-hmm.
That's independent of knowing that the gerbs, work out.
Sure, I mean.
So you haven't done that. You've called T-duality just the corresponding, well, I would call the Chern character and the flux.
No, we have done T-duality for n equals 0 supergravity, right? You have B field, you have metric, Busher rules, and you want to make sure that you get this together topologically consistent and differentially refined, and that hasn't been done before. That's what we did, right? And we reproduce, the Busher rules are reproduced in our formalism, right? That's all that we did, right? So there may be more, of course, you want to...
I'm afraid there's more.
Well, yeah, I mean, you can always extend it, but I think it's a good start. Yeah.
You're not understanding the problem, that's the thing.
Well, yes, I mean, but you have to start somewhere, right? And what has been... I mean, see, again, my motivation for coming into this is I want more examples of adjusted principal 2 bundles, right? And that is one. That's exactly one of the applications.
All I'm saying is you can't call it T-duality. You're sort of doing part of T-duality. That's what you're doing.
Sure, right. I mean, you can always go beyond, right?
Mm-hmm. Other questions, Chris?
Yeah, this is following on a little from the last question, which is going back to the example of the 3 torus with H flux and then T-dualizing, then the first two dualizations are straightforward. But then when you finally, I wanted to ask about the R space, the picture of the R space that you have. In the first few dualizations, you get bundles over a circle. But to get the R space, you need to look at bundles over the doubled circle. And I don't quite see how that fits.
I mean, here you would look at these augmented two groupoid bundles over a point, right? So it may not be sufficient.
But would you see the doubling of the circle in your picture?
Yeah, it is automatically in this TDN because you always the structure of TDN has 2 circles built in, right? So you have this R2N, Z2N, which is essentially
doubling the third circle.
Doubling the third circle, yes, you do. You do see that, of course. Because remember, we now use TD3, right? So here you have R6 and Z6, and what you should see this as R6 over Z6, so that gives you 1 to the 6, right? You double really all the circle direction to have T3 cross T3 in the fiber over a point, essentially, right? So you do see that in the group, yeah. But beyond that, I mean, the R space case is very shaky, I would say, right? So it's a question if it's one way of extending it, and I think that certainly this picture with the augmentation is certainly very promising. But what to put in G-1, our guess with the with the integrated embedding tensor is the obvious one. But you may want to go beyond that. Yeah, exactly.
Yeah. So I mean, my question is really understanding how the physics picture fits in with your picture. But maybe we can discuss that after.
Yeah. Okay.
Okay. Any other questions? Okay. If not, let's thank Christian again for the very nice talk.